So hi everyone, I'm Solal. As Panda said, I'm going to talk to you about automated verification of network function binaries. So the context here is software network functions, which are software implementations of network features such as a bridge, a firewall, and a NAT. And what we want to make sure is, first, they shouldn't crash, because that would take down the network. And second, they shouldn't have bugs, such as corrupting a packet. But more constructively, what we want is we want a specification that says what the network function should do. For instance, the IEEE has a document that states what a bridge should do. And if we could obtain a proof that a specific implementation of a network function obeys this specification, then we can get correctness guarantees about the state of the network. And so the way a network function works internally is that it has a piece of code that talks to some data structures to store state and to make decisions about a packet. For instance, a firewall might store flows and check if the flow is known, and if so, forward the packet, or otherwise drop the packet. The data structures themselves are too complex for automated verification, so they're beyond the scope of this work. What we're going to focus on is the network function code itself. And the hard part is how this code is going to interact with the data structures. So for instance, a piece of network function code might interact with a hash map and an array. And those data structures have contracts which specify how they must be used for correctness. For instance, indexing into an array requires an index that is less than the length of the array. And we also have to infer invariance across those data structures based on how the network function code uses them. So those invariants are not explicit, they are implicit, but we must infer them to avoid false positives. For instance, the hash map may be a flow table, and the array may be a cache. And it may be that the network function always adds stuff both to the cache and the flow table. So we don't want the false positive where our tool would say, oh, but if there's an item that is in the cache but not in the flow table, then there will be a crash. Well, that state may not actually happen in practice due to the way the network function code manipulates the data structures. And so we have to prove that the code obeys the contracts of the data structures by inferring all those invariants. And this is the hard part. So we have two main requirements for automated verification, which are, first, we want to support any data structure. Developers use all kinds of data structures. And second, operators deploy binaries, and they often don't have access to source code. Now, previous work required developers to use a set of very specific data structures that the tools knew, and the tools knew about which invariants those data structures could have. And the previous work also required source code, could not verify binaries. This work actually solves both these issues. So we allow developers to use any data structure they want, and we can verify binaries without the need for source code. The main takeaway I wanted to get from this talk is that describing data structures with maps, regardless of how they're actually implemented, enables the automated verification of network function binaries. So in the rest of this talk, I will talk about how we abstract data structures, then how we handle binaries without the need for source code. Then I will describe our implementation, some of our evaluation, and the limitations of our approach. First, data structures. So, let's say that you have a hash map. You could verify code using this hash map by hard coding the knowledge of that into the tool. Okay. Then we have a tree. You could add that knowledge to the tool. And you could add the knowledge to the tool of the invariance that can happen between the hash map and the tree. For instance, all of the keys in the hash map are also in the tree, or all of the values are also in the tree, and so on. OK, now you add a ring buffer. Now you have to add two more kinds of invariants. And you want to add one more data structure, a stack. Now you have to add three kinds of invariants. This doesn't scale. Instead, what we're going to do is we're going to represent all of these data structures as maps. This is a sweeping simplification. That means that now this is much more regular. Our tool only has to deal in terms of maps, and it only has to deal with invariants across maps. You can add any number of new data structures. As long as you can represent them with a map, our tool can understand them and can figure out the invariants that it can have with other data structures. So here's an example. Let's say we want to write a contract in terms of maps for the evict operation of a least recently used cache. So we're going to represent the state of this cache as a map from values to ages. This might not be how it's implemented, but this is how we're going to abstract it. Our precondition is going to be that since we want to evict something, there has to be something in the map, so the length has to be greater than 0. Then our postcondition, well, first, our result has to actually be in the map because we are evicting something from the cache. Then our new map is going to be the same as the old one minus the thing we evicted. And then the interesting part. We're going to say that for all of the values and ages in the map, the age is less than or equal the age of the thing that we're evicting. That's the least recently used part. And the interesting part about this is that this contract does not actually tell you how to implement an LRU cache. Even if you had implementations of those map operations like length and contains and for all, you could not just execute them to obtain an LRU cache. This contract tells you what the data structure does, but not how it does it. So even if this LRU is not implemented with maps, you can describe it with maps. So we also only require developers to write contracts in Python, which already uses maps as a fundamental data structure. They don't need to write fancy formulas. Now that we have contracts in terms of maps, we need to translate them. We need to translate those map operations into queries that a solver can decide. And the problem here is that we cannot just list all of the possible keys and values in a map. We cannot say, well, OK, so key K1 and value V1, key 2 and value 2, and so on, because we don't actually know how many items there are. There could be 0, there could be billions, and we don't want to make very, very large queries. The insight is that actually a network function only performs a few operations per packet, per iteration of the network function code. So what we're going to do is we're going to keep track of the items we know about, which are those explicitly manipulated by the network function in one packet processing iteration. And then the other items, however many there are, we're going to keep track of them as an invariant. So for instance, let's say that during one iteration, we abstract some operation as a get call on a map. So we get the value associated with key K1 in map M, and we get value V1. We're going to keep track of, OK, key K1, value V1 are in the map. Then we remove key K2 from the map. We're going to keep track of the fact that key K2 is not in the map. And for all of the other items, we're just going to keep track of an invariant to track our knowledge of them. So for instance, it might be all of the values are greater than 0. This scales because now, no matter how many items there might be in that map, we only need to track the items that we actually know about. The others are all represented with one invariant. This also means that now we can do invariant inference. Because if we represented a map as like one big formula, it would be difficult to figure out which parts of that formula are invariant across iterations. But now, we have known items that are manipulated in one iteration to help us. We can use them as templates. We can look at what the network function has done and say, OK, so in the known items, all of the keys added in map 1 are values in map 2. Does that hold across the unknown items? If so, we have found an invariant. Now, let me tell you about how we handle binaries without the need for source code. So again, this figure, we have network function code. It talks to data structures. If we zoom in a little bit, we have some control flow in the code, and it's also going to talk to some network primitives, like send a packet or receive a packet. So for instance, if the map contains the flow, then forward the packet, or otherwise don't. What we're going to do is we're going to perform symbolic execution to find all of the paths throughout this code. So instead of executing the code with a specific packet, we're going to execute it with a symbolic packet that represents all possible packets. And whenever we encounter a branch, we are going to explore both options and remember the choices that we made. So for instance, we might have one path that's like the packet is IPv4 and a bunch of other constraints. And in that path, we called map get, and the result was yes, and then we called packet forward. And then we have some other path where the packet was not IPv4, and some slightly different behavior happened. And then a bunch of other paths, and together, those represent all of the possible paths throughout the NF. So we have performed exhaustive symbolic execution. Now, that's nice, and what I've described is for source code. But at the binary level, we don't have this control flow information. We don't have all of these types. We just have a bunch of jumps. The binary could be obfuscated. So how are we going to deal with this? Well, the key observation is that the binary is still going to dynamically link with the data structures and the network primitives. And we can still observe the interactions that it has with its environment, with these data structures and network primitives. Because when the binary, for instance, calls a map_get function, that corresponds to a symbol that it has to export in order to link against the data structures. So we can still use the interactions between the binary and its environment to fully define what the network function does, because we have this information of which interactions happened and what conditions held at that point. So we still have this notion of a path where the binary called map get with this part of the packet, and then the map said yes, and then it called packet forward. And we know what the arguments are because this is a standard ABI. Now that I've talked to you about how we handle binaries, let me quickly describe our implementation. So we built a tool that we call Klint, which takes as inputs a network function binary and a set of contracts for the data structures that the network function binary uses. Klint is going to translate those contracts, as I described earlier, by translating the map operations so that they can be understood by the symbolic execution engine we use, which is Anger, an existing engine. And so Anger is going to symbolically execute the network function binary, and anytime there is a call to a data structure, since data structure code is too complex for symbolic execution, we're going to execute the translation of the corresponding contract instead. Then Klint is going to infer the invariants that hold on the network function code, and this is going to lead to a set of paths. Now, we could stop there because that already tells us, if we have finished this step, that there are no crashes, such as a null pointer dereference, and that the binary is memory safe. But we can also give Klint a specification. And now Klint can then check that every single path obeys the specification. And because we have obtained every single path throughout the code, we know that if all of the paths obey the specification, then the entire binary also obeys it. Otherwise, we get a counterexample. Now for our evaluation and our limitations. So there is more evaluation in the paper, but the gist of it is that we verified 6 network functions written in C and 1 in Rust. The reason we verified a network function in Rust is to show that our approach works on any compiled network function, not just those compiled in C. It takes less than 2 minutes to verify a network function. And that's using our single-threaded prototype on this very laptop I'm using to present. You don't need fancy hardware. You don't need tons of cores. The interesting part is that the performance of our verified network function is actually way better now, because we were able to prototype new data structures that are much faster because they're specialized for our use cases. In the past, if you wanted to do that, you would have had to add the knowledge about your data structure to the verification tool. You would have had to write thousands of lines for the proof of the invariance that your new data structure could have with other data structures. And after you've done that, then maybe actually your NF is not correct when verified with a data structure. So now you have to spend another month writing more invariants for a slightly different data structure. With Klint, all you have to do is write your new data structure, then write contracts for it in terms of maps, and the tool takes care of the rest. So now our network functions are faster than previous verified network functions, and in fact, they're faster than the baselines like click that previous work used but could not beat. At this point, you might ask, well, that's great. Why are you only verifying network functions? And the key here is that network functions have an environment that is only a small number of networking operations, and they're rather shallow in the sense that if you send a packet, this does not actually affect what packets you might receive, because you can receive any packet at any time. So we can model the complete behavior of all networking operations in our tool once, and then use it for verification. If you wanted instead to use this approach to verify, say, a Linux program, you would have to model all of the dozens of system calls in Linux and all of the semantics that they have. Like, for instance, when you have opened a file, then this changes the behavior of future system calls that deal with this file. That would take you a very long time, and also Linux is not static. It would update, so you would have to update your semantics frequently. Now, maps are great, and they are a good fit for most data structures, but they're not perfect. Sometimes the contracts can be a little bit awkward for some data structures. The more interesting limitation is that there is still some complex code that cannot be automatically verified and also doesn't make sense to abstract in terms of maps. So typically, a regular expression engine for an intrusion detection system is something that is still beyond our reach. So in summary, we verify network function binaries that use any data structure as long as it has contracts in terms of maps. And we translate those maps into queries by tracking the known items explicitly and the unknown items as an invariant. This scales and also enables us to infer invariants. So you can find the paper and the code at this URL. Thank you.